Our next unit is going to be on Newton's laws. And so we're going to start off here with Newton's laws 1. And in this unit, or in this lesson, what we're going to look at are two things. First thing is the fairly obvious one, which are Newton's laws of motion. And the second is going to be static forces. So let's talk a little about Newton's laws of motion to start things off. So in 1687, the British scientist Isaac Newton, sometimes you hear him Sir Isaac Newton, published 3 laws which govern the motion of bodies in his Philosophiae Naturalis Principia Mathematica. This is usually just known by sort of the middle section of the name here, just Principia is the term that's used. This covered a number of different topics. It was written in several volumes, but for what we're talking about right here, we're only going to talk about these laws of motion that he derived. He determined basically just before this time. So these 3 laws that we're going to talk about, Newton's 3 laws, are valid under certain conditions. The first thing is they're valid for rigid bodies. And so when we say rigid bodies, we basically mean things that don't deform. And so they may not necessarily work out very well for things that basically they'll stretch whenever you apply a force to them, or can bend when you apply a force to them. They apply for these rigid bodies if they can be treated as a single point, what's called a point mass. And so that just to generalize it, so if we know we have some box right here, we can treat it as if, and it's say a 3 kilogram box, we can treat it as if that whole thing is all at one point in the center of mass, and so that way we can apply forces to it in various directions. And so that has to be true. And it has to be true at the reference frame, which is from where the measurements are made, is not accelerating. And so basically, if you can't take measurements while you're accelerating by whatever you're measuring here. That doesn't apply here. Which is very rarely is that ever the case. Normally you're either sitting still or moving at constant velocity with your whatever you're measuring. And then the last thing is sort of gets to Einstein here a little bit, which is that speeds can't be near the speed of light. And so they have to be sort of regular speeds, everyday type stuff. And so despite all these things here that look like they're sort of exceptions, Newton's laws actually apply in most everyday situations. At least we can use them sort of in a generalizable sense. So let's go ahead and take a look at Newton's first law. Newton's first law basically says the velocity of a body remains constant unless it is acted on by an outside force. Sometimes you'll hear this as an object in motion will remain in motion at a constant velocity unless an outside force acts on it. So what this means, pretty straightforward. If there is no external force on an object, and when we say force, we basically mean a push or a pull. So in forces, that's basically the meaning here. A push or a pull on an object. It's going to be, the unit we're going to use here is going to be newtons for obvious reasons. Symbol is going to be capital N right there. A newton is roughly about the weight of a single apple. You can sort of think of it that way. It's a good mnemonic. So basically, this is sometimes, so if there is no external force on an object, no external push or pull, it will not change velocities. And so if I have an object that's moving along at a constant velocity, that's either sitting still or moving at like 5 meters per second, and there is no external force, the total force is 0 on it, then it will keep going at that same velocity. If it's sitting still, it'll remain sitting still. If it's going at 5 meters per second, it'll continue going at 5 meters per second. And so we can then take sort of the, I think it's the converse to that. If an object is not accelerating, then that means the total, or the net is the term we'll use, force on that object is 0. And so if you look and you see an object, it's sitting still, therefore it's not accelerating, then you know the total force on that object has to be 0. These are consequences of Newton's first law. And so this is Newton's first law. Let's go on to his second law. So Newton's second law says that a body's acceleration will always be directly proportional to the net force on the body, but inversely proportional to its mass. And so if you do have a net force, then the object will accelerate, and it's going to accelerate in a way that's directly proportional to that net force. And it's going to accelerate in a way that's going to be inversely proportional to its mass. And so easier to sort of explain this one mathematically. And so here it is right here, that the net force on an object, F net, is equal to mass times acceleration. Now, looking at this, there should be a couple things that stand out. First thing is that this is not just any force, this is a net force, the total force on the object. When we take every last external force and we add them all up. And so so if I have, an object that's sitting on a table, it's going to have a force of gravity on it. And let's say someone's pushing on it, so it's going here. And let's say there's friction on it, it's going here. And there's a force upward called the normal force, the table pushing upward on it here. If I want to find the net force, I have to add up every last one of these. And since they're vectors, I have to add them as vectors. That's the other piece here. See, we have a vector sign here and a vector sign here. Force is a vector. It has magnitude and direction. Acceleration is a vector. It has magnitude and direction. And mass is just a scalar. It's just going to scale up that acceleration, scale up that force that we get right there. So what this also means is that whatever direction your acceleration is in, your net force has to be in the same direction. It can't not be. It's not possible to have a net force that goes one direction and acceleration that goes a different direction. So F net equals ma. Sometimes you'll just see this as being just F equals ma like this, but they are vectors from force and mass, and this is a net force. Now, if you only have one force on an object, it just turns into F equals ma. But this is basically Newton's second law. So F net is the net or total force in newtons. We talked about those before. M is the mass in kilograms, and the A is acceleration in meters per second squared. That's going to be our SI system units we'll use here. So if this is true, sort of third point, if an object is accelerating, then it must have a non-zero net force in the same direction and vice versa. If you see something that's accelerating, automatically you know that object has a force on it, an total external force that's not zero. No questions. And then the last one here, the net force, we sort of define it here as we talked before, is the sum of all forces on an object. It is possible to have a force on an object without an acceleration. Take the case where, once again, talk about our box here. This time our box is going to be just sitting here. Has a gravitational force downward, has a normal force upward here. If those two forces are equal, then when you add them up, since they're in opposite directions, they're going to cancel out. We get a net force of 0 in that case. And so there would be no acceleration, even though there is a force on it. Gravity applies to this. The reason why is because this is a net force that we're discussing here. So as long as the net force is 0, you'll have no acceleration. And so that's basically Newton's second law. Newton's third law says this. For every force, there is an equal force in the opposite direction. Sometimes you hear this as for every action, there's an equal and opposite reaction. Basically, mathematically, we have that the force of A on B is equal to the negative of force B on A. And so in the case where I have my object right here sitting on a table, and let's say that I am going to, because I can't draw very well, I'm going to push a plunger against my object. This plunger is going to exert a force onto the block. Now what that means is that the block must also exert a force onto the plunger, and that the magnitudes of those two forces are going to be exactly the same. You can think of it sort of like this, is that you can't touch something without being touched. If I put a force of 5 newtons on a blackboard, then that blackboard has to be exerting a force of 5 newtons on me. Now note that this doesn't make a difference whether or not the object moves. If I basically put a force on a desk to make it start moving, to make it accelerate, is that that desk is still exerting the same force back on you. It doesn't matter whether it moves or not. It's always true that if you exert a force on something else, it will exert that same force simply in the opposite direction on you. And so these are force pairs. And so another typical example of this is that we have a box on a table, right, or a book on a table right here. It's a very fat book. It's a dictionary or something. If a table exerts a force upward on a book right here, then the book must also exert a force on the table, a force on the table right here. They have to be equal and opposite. Now, we have to be careful with this, is that if it's the force of the table on the book, the equal and opposite force is the force of the book on the table. So sometimes you can confuse this with the fact that sometimes two forces are equal. Like say gravity is pulling down on this book. That's why I drew here originally. It was actually more gravity pulling down, and that force is equal to the force of the table on the book. But that's not the equal and opposite force, because the gravitational force is not the force between the book and the table. It's the force between the book and the earth. It's what the earth pulls on the book. And so if the earth pulls on the book with a force of, say, 5 newtons, then that would mean that the equal and opposite force is the book has to be exerting a force of 5 newtons upward on the earth. anytime you set these up looking for force pairs, you always have to remember that this is basically AB and BA, that it's the force of A on B is equal and opposite the force of B on A. There always have to be the same two objects exerting forces each other for these equal and opposite forces. Even though sometimes coincidentally you may get ones that are equal and opposite but are not Newton's third law pairs, force pairs. So that's basically Newton's third law. These are the three laws that we have here. So let's take a look at some simple cases first. So let's talk about what happens if, when you look at all your forces, they add up exactly to zero. You have a net force of zero. This is called a static situation. So a static object, the word static, refers to an object which is not moving. So kinetic is the opposite of that, an object that is moving. So if an object is not moving, then the velocity is zero. So therefore the acceleration is zero. And if the acceleration is zero, this is the average. The velocity, it's not moving; it has zero acceleration. And if the acceleration is zero, the net force has to be zero on the object. That's Newton's second law stuff. Newton's first law as well. So forces which sum to zero are called static forces. Whenever we talk about them as a whole, we wouldn't call each individual force a static force, but we'd say all of them are static if we add up all these forces and they all cancel out each year. So in cases of static forces, missing forces can be found by simply setting the summed forces equal to zero. And so the net force in this case is equal to the sum of each of the individual forces, and they equal zero if it's static. And so the example here, if we have a couch right along here, and we have one man is pushing this couch with a force here of 50 newtons, and another man is pushing the couch with a force of 30 newtons, and it tells us that the couch doesn't move. If the couch doesn't move, that means the acceleration is zero, which means that the net force has to be zero. So there has to be some other force which is pushing back. In this case, that's likely to be friction. And so the question is, what is this frictional force? Well, to work this out, we'd say, well, we know the net force is zero, so let's add up our forces here. So pushing, and we'll say this is the positive direction, and the other way is the negative direction. And so if we're doing this, we'd say in the positive direction we have 50 plus 30. Those are our two positive forces. And then minus our force in the other direction, which is the frictional force, which is going to be equal to zero because this is not moving. It's not accelerating. These are static forces. And so if this is true, all we have to do is rearrange. Move the FF to the other side, so the frictional force is going to equal to 50 plus 30, which is 80 newtons. And so this must have a frictional force of 80 newtons in this case. So this is basically how you set things up in cases of static forces. Now, in our example right here, we're all moving in one direction, but the same thing is going to apply whenever we have forces in opposite directions. I have forces here, here, and here, say on a box. Is that what we know here is that if I look at all the forces in the x direction, if it's a static situation, if it's not accelerating, all my x forces have to cancel. And so in this case, my x forces would be this guy right here, and then the x component of my upward force in that case. And so I know that those two forces would have to add it up equal to zero. And the same thing is true for my y forces. This y force right here and this y component right here, if I add those two up, they'd have to equal zero. And if I know some of these forces, by setting them equal to zero, I can add them up and sort of solve. And so this is sort of how we're going to use static forces. They make sort of situations a little bit easier to start things off. So let's actually look at some examples of how we might go about solving problems using static forces. So let's say a 25 kilogram sled is being pulled up a frictionless 25-degree ramp by a rope. What tension force on the rope is needed to keep the box in place? I guess I should have, actually, I guess it's not sled, it's be a box. 25 kilogram box right there. So a box is being pulled up a frictionless. So we have an incline right here. Here's our incline. We have a box that's on that incline right here. The angle on it, we're told, is 25 degrees right up here. It's also a 25 kilogram box. And there's a rope which is pulling it up. And so it's going to be applying a force. There is gravity, which is coming down, that's applying a force. And there is also a force which goes upward here, which is our normal force. In this case, the normal force being the force of the surface up on the box. Remember, there's always, anytime you put an object on a surface, there's a normal force or perpendicular force that goes up. It's the reason why when you set a pencil on a table, it doesn't fall through. So those are our three forces on this right here. Now, question is, what tension force in the rope? So we're looking for the tension right here. That's what we want to find. So to do this, let's go ahead and let's redraw this. Let's rotate the coordinate system. And so we're going to rotate by 25 degrees clockwise. And so now here's our box all rotated. It has a gravitational force which, whoops, does not go down. That would be wrong. Get rid of that. Try that again. Back to the drawing board. Literally. So in this case right here, we have a normal force which goes up in our rotated system. The tension force is going to go in this direction. So here's our tension. Here is our normal force right here. Gravity used to go straight down, but now that we've rotated, it's now going to go off at an angle. And so the angle that this is going to go at is going to be such that it can be broken into two components. So a component this way, a component this way. And so that's going to be our force of gravity right along that side right there. So these are our forces on the object. So the question is, what tension force on the rope is needed to keep the box in place? So let's take a look at this. Do we know any of these existing forces? We're looking for tension, so we know we don't know that. Normal force tells us nothing about, but it does tell us that the box is a mass of 25 kilograms. And so let's look at gravitational force. And so if we look at the gravitational force, Fg, right here, the gravitational force is provided by the Earth pulling on the box downward. And we know if it's near the surface of the Earth that this force is going to be pulling on it so that its acceleration, if it were in free fall, would be 9.8 meters per second squared. And so when we set this up, what we can do is we can basically say that the force of gravity on an object is going to be equal to its mass times the acceleration due to gravity, which we're going to call lowercase g in this case. And so then that the force of gravity on the object is going to be its mass, which is 25 kilograms, times acceleration due to gravity, which is 9.8 meters per second squared. And so if we solve for the force of gravity off of this, we end up getting is 245 newtons if you do the math on it. So force of gravity is 245 newtons. We've got that. So let's go ahead and see if we can find what the two components of that, because that just gives us that diagonal vector, right over there. We want to find what the x and y components are. Specifically, since we're looking for tension, we know this box is, it says the box is being held in place. It's not accelerating, which means that the x components, if we add them up, will be 0, and tension is only an x component. So really what we're going to be looking at here is that we know that the net force in the x direction is going to be equal to 0, which means that, we're setting this up, that the tension, which we'll call in the positive direction, minus the gravitational force in x has to equal 0. And so if we can find Fgx, we should be able to find the tension. And so to find Fgx, we'd have to look back up here and we would say, okay, this angle inside here is going to be 25 degrees because that's how far we've rotated it. It was originally straight down, now it's angled over. We rotated it by 25 degrees. And so if we want to find that x component down there, then it's an opposite, so it's going to be sine. And so then Fgx would be simply equal to Fg sine of our angle, which in this case is 25 degrees. And so solving for Fgx, as Fg is 245 newtons, so Fgx would be equal to 245 newtons times sine of 25 degrees, right up there. And so if we solve for Fgx, put those into a calculator and work them out, and I get 103.541 newtons. And so that's going to be my x force of gravity, the force of gravity component of x. So my tension would have to be not equal. Tension minus 103.541 would equal 0, because we know that the total net force in the x direction is 0 because it's being held in place, it's not accelerating. So move it around, we find the tension would be equal to 103.541 newtons. Significant figures here, 2 right there, so therefore it's going to round to 2 sig figs. So our tension force to keep this box in place would have to be 100 newtons. And so that's an example of a statics problem. That's how you go about setting that up. So let's take a look at a different one. All right. So, wait for the ding. A 550 Newton person stands still with each foot on a different scale. Their right leg is at an angle of 75 degrees from the ground, and their left is 60 degrees from the ground. What downward force in newtons does the right foot scale read? And so we have a person who has two scales, one here and one here, and what we're told is that their right leg is at an angle of 75 degrees from the ground, and their left leg is at an angle of 60 degrees from the ground. I didn't have him stand on the scale very well, but that's him on the scale. So we know that this angle right here for the right leg, from his perspective, he's facing us in this case, so it looks left to us. But so on that leg is 75 degrees, and on the other one is going to be 60 degrees over on that side. And so that's their legs. There's the person. Really don't care. It's a little out of scale, but you get the idea. So basically, this person's standing with the legs on either scale, but he's put sort of favoring his left leg. He's putting more weight onto his right than he is on his left. And so as a result, basically that angle is smaller. Just like, if you stand and put your weight all into one leg, you'll see the angle decreases on the leg that you're putting your weight onto, and it increases, or sorry, the angle from the ground increases on the leg you're putting your weight is. It's more perpendicular, and there's more angle or less angle toward the ground for the leg that you're favoring, when you're not putting weight on. And so the question is, what's the downward force in newtons does the right foot scale read? And so if we were to sort of put this person as sort of a point here, then we would say that there's a force downward of gravity. Now, what is that gravitational force? Well, it tells us 550 newtons. So there's a 550 Newton force that's going down right there. We have this leg is pushing up on him in this angle, this leg is putting up on him in that angle. And so our forces here are going to be one force right here, which we're going to, just for the purpose of doing this, we'll say it's Fr is our force on this. And we have another force that's on this guy, which is going to be sort of over here. That's the left leg pushing up. We'll call that Fl. Now, we know that in order to solve this, we're going to have to break this into components. And so to break this into components, we'll do Fr has a y component, or an x component. Fl has an x component. And then we'll do the same thing for y, is that Fr has to have a y component, and Fl has to have a y component right here. Now, what we know is the two green arrows are two x components, because the fact the person is standing still, not accelerating, are going to have to cancel out. So our two green arrows have to be equal and opposite in this case, not because of Newton's third, just because of the fact it's static. And we know that the y components are also going to be 0. So our two red arrows up, the two upward forces of the legs, have to equal out the weight of the person, 550 newtons. If not, the person would collapse. His legs would give out. And so this right here is basically our situation here. So the question is, what downward force in newtons does the right foot scale read? And so really, since we're talking about the right foot force in newtons, that's going to be, it's a downward force. That's going to be basically this red arrow right here. Because if the scale is exerting a force upward on him of that red arrow, the y component of the right foot force, then the right foot has to be exerting a same equal and opposite force downward on the scale, and so that's what it's going to read. So that's what we want to find. So in this case, let's set up our x's and set up our y's. And so to do this, let's look at x first, and then let's look at y. So for our x forces, we know that basically f right foot x and f left foot x are going to be basically equal to each other. Now, to figure those out, we'd have to know the angles. Fortunately, we know the angles. In this case, it told us in the problem that the right foot is at an angle of 75 degrees. The left foot comes at an angle of 60 degrees from the ground. And so to solve for our x component of the right foot, we would say Fr times, in this case right here, it's the adjacent over hypotenuse, and so that's going to be cosine. So Fr cosine of 75 is going to have to be equal, to make sure they balance out, to Fl, which is also an adjacent here for that green arrow right here, so it's going to be cosine of its angle, which is cosine 60. So Fr cosine 75 equals Fl cosine 60. And then for the y direction, we have two upward forces, which are going to be basically Fr sine of 75. that red arrow pointing upward, plus the other force that's pointing upward, which is FL sine of 60. And if we add these two up, they have to basically combine to cancel out the force downwards, the gravitational force, which is 550 newtons. All right, so we have this set up here. Now, we have two variables here, two equations. We should be able to substitute and solve. Let's take a look at our simpler equation, which is the top one, and let's go ahead and let's say we're going to solve for FL. And so if we solve for FL, that means we basically have to divide both sides by cosine 60, and so we get that this is FL is equal to FR cosine 75 divided by cosine 60. And if you do this just in the calculator, you get that FL would be equal to 0.5176 times FR. So 0.5176 is cosine 75 divided by cosine 60. So we now know what FL is in terms of FR. So let's go back and let's plug it into our equation here. So back into our y equation. So we can get all this in terms of FR. So we have FR sine of 75 plus, not FL anymore, we're now going to use 0.5176 FR, right there, times sine of 60 equals 550 newtons, right there. And so we can combine, let's go ahead and get these into non-sine numbers, regular numbers, just combine them here. So we end up with sine of 75 is 0.44828 times FR plus my next one here, when I take 0.5176 times sine of 60, oops, that is wrong one. Give me a second here. I put the wrong one on here. That's FL, not FR. Try that again. All right. We do this here. 0.517. Okay. Sine of 75 is not that. Sine of 75 is 0.9659. 0.9659 times FR. Plus, when I take 0.5176 times sine of 60, that's when I get 0.44828. We're just doing the math on this right now. Equals 550 newtons right there. I can combine these two together. Whenever I do that, I get right at 1.414 FR equals 550 newtons. And just by relative mathematic coincidence, if you notice very carefully, 1.414 happens to be the square root of 2. So just in case you were wondering here, that is coincidence in this case, just based on, well, not based on the numbers that we have, it just happens to give that value. It's nothing special about it in this particular problem. And so solving for this, we can solve that FR, based on this, would have to equal 388.909 newtons. Now, this is going to be the total value of FR, not, so basically what the leg's pushing up, but that's got both an X and a Y component to it, is the part that's pushing down the scale is only the Y component. And so to find FRY, we'd have to have FR times, we said, sine of 75. Right here, and whenever we do that, plug those numbers in, we get 375.657 newtons. Rounding here, two significant figures here. The angles are at 2, they really don't make a difference here, so 2 would be our answer here, so we get 380 newtons. And so the scale is going to read 380 newtons on the right side, on the right foot, if this is a 550 newton person standing with right leg at 75 degrees from the ground and left leg 60. So this would be an example of a statics problem. These are basically how you set them up. So that is it for today's lesson.